Example 8. Find the McLaurin series for f of x equals open 1 plus x closed to the power k, where k is any real number. Solution: arranging our work in columns, we have f of x equals open 1 plus x to the power k. F of 0 equals 1. The first derivative of f of x equals k open 1 plus x closed to the power k minus 1. The first derivative of f of 0 equals k. The second derivative of f of x equals k open k minus 1 close open 1 plus x close to the power k equals 2. The second derivative of f of 0 equals k open k minus 1 close. The third derivative of f of k equals k open k minus 1 close open k minus 2 close open 1 plus x close to the power k minus 3. The third derivative of f of 0 equals k open k minus 1 close open k minus 2 close. The nth derivative of f of x equals k open k minus 1 ellipsis, there's a close, ellipsis, open k minus n plus 1 close open 1 plus x close to the power k minus n. The nth derivative of f of 0 equals k open k minus 1 close ellipsis open k minus n plus 1 close. Therefore, the Maclaurin series of f of x equals open 1 plus x close to the power k is the sum from n equals 0 to infinity of the nth derivative of f of 0 over n factorial x to the power n equals the sum from n equals 0 to infinity of k open k minus 1 close ellipsis open k minus n plus 1 close over n factorial times x to the power n. This series is called binomial series. Notice that if k is a non-negative integer, the terms are eventually 0, and so the series is finite. For other values of k, none of the terms is 0, and so we can try the ratio test. If the nth term is a sub n, then the absolute value of a sub n plus 1 over a sub n equals the absolute value of k open k minus 1 close ellipsis open k minus n plus 1 close open k minus n close x to the power n plus 1 over open n plus 1 close factorial times n factorial over k open k minus 1 close ellipsis open k minus n plus 1 close times x to the power n equals the absolute value of k minus n over n plus 1 times the absolute value of x equals the absolute value of 1 minus k over n over 1 plus 1 over n times the absolute value of x approaches the absolute value of x as n approaches infinity. Thus, by the ratio test, the binomial series converges if the absolute value of x is less than 1, and diverges if the absolute value of x is greater than 1. The traditional notation for the coefficients in the binomial series is open k and n close equals k open k minus 1 close open k minus 2 close ellipsis open k minus n plus 1 close over n factorial. And these numbers are called the binomial coefficients. The following theorem states that open 1 plus x close to the power k is equal to the sum of its Maclaurin series. It is possible to prove this by showing that the remainder term big R sub n of x approaches 0, but that turns out to be quite difficult. The proof outlined in exercise 85 is much easier. Number 7, equation 17, the binomial series If k is any real number and the absolute value of x is less than 1, then open 1 plus x close to the power k equals the sum from n equals 0 to infinity of open k n close. K is over n, but not in division. It's not a division sign. And multiply that by x to the power n equals 1 plus k x plus k open k minus 1 close over 2 factorial times x squared plus k open k minus 1 close open k minus 2 close over 3 factorial times x cubed plus ellipsis. Although the binomial series always converges when the absolute value of x is less than 1, the question of whether or not it converges at the endpoints plus or minus 1 depends on the value of k. It turns out that the series converges at 1 if negative 1 is less than k, and k is less than or equal to 0. And at both endpoints, if k is greater than or equal to 0, notice that if k is a positive integer and n is greater than k, then the expression for the binomial series open k and n close contains a factor open k minus k close. So the binomial series open k n close equals 0 for n greater than k. This means that the series terminates and reduces to the ordinary binomial theorem when k is the positive integer. See reference page 1.